Xilinx is very excited to announce a new series of Telco Accelerator cards specifically designed for 5G virtual baseband units and O-RAN compliant platforms. FPGAs are great for offloading line rate and compute-intensive functions. The first card in this series, called T1, solves the two most commonly requested offload functions, Fronthaul termination and Layer 1 Hi-Fi, in a compact 75-watt card. The card brings to bear significant signal chain horsepower, which frees up your general-purpose processors for edge compute tasks such as video streaming, gaming, or automotive services. Let's take a closer look at the primary accelerated functions of this card. The most common vBBU function we get asked to accelerate is the Layer 1 LDPC FEC, which is compute-intensive and not well-suited for traditional processors. Thankfully, the RF sock device on this card includes a standard cell ASIC block called the SD-FEC, specifically designed to tackle the LDPC at a high throughput, low latency, and low power envelope. In addition to LDPC, the card also offloads the HARC function, which is memory intensive and if not accelerated can bog down the traditional front-side bus of a telco server. The T1 card solves this problem by managing the HARC tables in onboard DDR memory so the processor doesn't have to. The reference design includes queue-based DMA and PMD drivers, rate matching, LDPC, FEC, encoders and decoders, code block CRC, and the HARC management using the DDR. For ease of integration, the card's reference design is plug-and-play with the FlexRAN software stack through vBBU APIs, which is the industry standard starting point for many 5G software deployments. So now let's look at the performance achieved with this T1 card. The server used is a Dell R740 with a Xeon Gold 3.8 GHz processor. This is representative of a typical server used in a 5G O-RAN deployment. The demonstration compares the LDPC FEC, rate matching, and HARC performance of the Xeon with and without the T1, running FlexRAN software to execute these functions. You can see the Xeon processor core achieves 0.718 gigabits per second encode and 0.183 gigabits per second decode, with a latency of 45 microseconds and 62 microseconds respectively. Next, we'll enable the vBBU APIs to offload these same functions to the T1 card. With the Layer 1 functions offloaded to the T1 card, you can see the encoder performance jumps to 17.8 gigabits per second, the decoder to 7.8 gigabits per second, with more than a threefold reduction in latency. Adding the T1 card to the server provides significant performance gains. You can see the LDPC decode function is accelerated by 24x and the encoder is improved by 42x. The T1 also includes a separate MP sock device to manage the Fronthaul optical connections between the radio unit and the distributed unit, specifically eCPRI with an optional O-RAN framer and hardware. 5G Fronthaul requires stringent timestamping accuracy, which this card provides, including holdover with master mode synchronization in the event of a GPS clock failure. Here you can see the PTP master clock interface, which is implemented at the front-end PHY, providing an accuracy of around a nanosecond. This card has two SFP28 optical cages for a total of 50 gigabits per second of Fronthaul optical termination, with the option to support primary and redundant port failover in high reliability modes. The reference design includes the PTP timestamping, eCPRI framers and deframers, O-RAN framers and deframers, which provide the M, S, C, and U-plane radio data pre-classified to the host as DMA queues. For ease of integration, the design utilizes industry-standard DPDK drivers to control the networking functions of the card, as is typical in SmartNIC deployments. Now let's look at the Fronthaul performance achieved with this card. This is the same setup we used in the L1 demonstration. To show the Fronthaul performance of this card, we will be simulating two 5G remote radio units, each a 4 TRX MIMO radio with an OBW of 100 MHz. In this demonstration, both radios are daisy-chained onto a single 25 gig optical port. Typically, the second port would be used for redundancy, but it can also be used to connect to more radio units depending on the desired deployment. In this demo, we are simulating a full stream of traffic and verifying that the T1 card correctly separates the S, C, M, and U-plane traffic from the RU stream and places the traffic on the appropriate DMA queue. With the traffic running, we can see the queue counts incrementing as expected in the Xena Network Traffic Analysis tool. Unlike with traditional Ethernet NICs, this Fronthaul design can process the O-RAN traffic at line rate in the T1 hardware, freeing up the server CPUs for more interesting software at the edge tasks. When designing this card, we focused heavily on ease of adoption and integration. These cards are available with pre-validated reference designs from our industry partners. In fact, the demo we just saw is a reference design created by preferred partner vBBU. Just buy the card and the reference design and start software integration work right away. We believe that by streamlining the technical and commercial complexities of multi-vendor RAN, we will all see Open RAN become mainstream sooner. We hope you enjoyed the demonstration of this T1 card, the first in a series of telco accelerators from Xilinx. Thanks for watching.